Here is a problem number 8, investigation problem that I have the deepest appreciation for. We are required to complete this row, this one, and also this one as specified by the statement of the problem. The series column contains the sum of cubes up to and including the number in the n column. So we have right here the sum of cubes. As a matter of fact, this is just a single cube. But what do we have here? 1 cubed plus 2 cubed. We have 2 right there. So 1 cubed. What about this one now? 2 cubed. Then we go 3 up to 3 cubed. 4, we go up to 4 cubed. Therefore, what do we imagine here? 5, we will go up to 5 cubed. In the n column, we have 5. The series will have the cubes up to and including 5. No problem with that one. All formulae are the same with exception of those numbers that are in the sequence, and the sequence is determined by the number in the n columns. Notice that every single thing that we have here is the same. 4, 4, 4, 4. Then we have 1, 2, 3, 4, the numbers that we have here, and we have 1, 2, 3, 4, the numbers that we have here, but everything else is the same. 1, 1, 1, and we have the squares. Everything is the same with those exceptions. Therefore, we will make use of the similarity and pay special attention to the differences. So 5 squared over 4, 5 plus 1 all squared, n squared over 4, n plus 1 all squared. The other formulae will be the same as the others, with the exception of the numbers that are the same values as those in the n column. So we have n, n squared, n. We have 5 squared and 5. No problem with that. The values in the sum columns may be determined by adding the numbers in the adjacent series or by using the formula. The formula will take less time and effort. We need to put the sum right here. So we could find the sum of 3 cubed, 2 cubed, 1 cubed, 2 cubed, 3 cubed, 4 cubed, all the way to 5 cubed. But I think that we may progress a bit more efficiently if we make use of the formula that we have right here, or this one. 5 squared over 4, 5 plus 1. 5 plus 1 is equal to 6. When we square that, we get 36, and we have 5 squared is 25. So 25 over 4, 36. We are multiplying by 36. We may say 4 into 36, making our life a little bit easier. 4 into 36 is 9. 25 times 9, and that is equal to 225. Anything else to be completed? Of course, this row. 8 squared over 4, 8 plus 1, all squared. 64 over 4, and multiply that by 81. But 4 into 64 is 16. So 16 multiplied by 81, and we have this number that turns out to be 1,296. What do we imagine will go right here? 8, of course. Probably the easiest thing to figure out is that an 8 should go right there. The unique number in each formula is always equal to the number that is in the n columns. So that is the difference between this one and this one. These numbers that we have right here, and we take that for granted. Before attempting to solve the other part of the problem, let us see how we could have used another pattern in finding the values of the sums of cubes. We could have used another pattern. This pattern is not so blatantly given or seen in the table. We could have made use of what are known as triangular numbers. These numbers are related to the number of objects that may be arranged in a triangular format. The first triangular number is 1. If we add another 2 stars, the objects are still in a triangular format, so 1 plus 2 is equal to 3. The second triangular number is 3. Notice that they are in a triangular format. How many other stars do we add in order that we may have another triangle? So add another 3 stars, and the third triangular number is 6. Notice that we started with 1, then add 2, then add 3. We will add 4, then 5, etc. So add 4, and what do we know? We have the fourth triangular number, and that fourth triangular number is 10. Then if we add 5, so we add 2, then 3, then 4, then 5 is 15, then 6, 21, then 7, 28, then 8, 36. Remember the triangular numbers as we move to the other slide that contains our initial completed table. As a matter of fact, the triangular numbers will be presented on that slide in order that we may make the connection between the values in the sum column and the triangular numbers. The 7th slot is missing, but take note that each of the sums are the squares of the respective triangular number. The first triangular number is 1. We square that, we get 1. The second triangular number is 3. Square that, we get 9. The fourth one is 6. Square that, we get 36. The other is 10. Square that, we get 100. The fifth triangular number is 15. Square that, we get 225. Then the sixth one is 21. Square that, we get 441. And then we see that we have the 7th one missing, and then we have 8. But in the sum column, we have the square of the associated triangular number. We see that the first sum is the square of the first triangular number. The second sum is the sum of the second triangular number. The third sum is the square of the third triangular number. Before attempting to solve this part of the problem, let us write down the formula. So we have the formulae given to us, and we will write them down so that we can make reference to them in solving this part of the problem. Notice that what we have in each case is the square root of the sum of cubes. So what we have in each case is the square root of the sum of cubes. So when we add the cubes, we get 9. The square root of 9 is 3. When we add the cubes, we get 36. The square root of 36 is 6. When we sum the cubes, we get 100. The square root of 100 is 10. What do we know then? Determine the value of x for which 1 plus 2 plus 3 plus 4 plus 5 plus 6 is equal to the square root of x. What do we imagine? We imagine that we will make a reference to the associated sum of cubes. This one. In each case, we have the square root of the sum of cubes. We have the square root of x. Therefore, x is the sum of the associated cubes, as we said before. So we have the sum of cubes, as we have it right here. 10 is the square root of the associated sum of cubes. So x will be the square root, or x will be the associated sum of cubes. The associated sum of cubes for this series will be what? 441. Right. So x is equal to 441. We need a formula for the following sequence. That one. And I think that we should make reference to this one. In each case, we have the square root of the sum of cubes. So here we have the sum up to n. If we have the sum up to n, what do? We make use of the associated sum of cubes, which is this one. So the answer is the square root of the sum. All we need to do is take the formula for the sum and find the square root of it. So this is the formula for the sum of the associated sum of cubes. So this formula is the associated sum of cubes. Therefore, what we need to do, like we have right here, and in these cases, we need to find the square root. Finding the square root, pretty straightforward. The square root will eliminate all of the squares, and the square of 4 is 2. Do not forget that taking the square root will eliminate the squares. The square root of n squared is n. The square root of n plus 1 all squared is n plus 1. And the square root of 4 is 2. Turns out to be n over 2 n plus 1. So there we have it. If we add from 1 all the way up to n consecutive counting numbers, that sum is found by the formula n over 2 multiplied by n plus 1. If we are finding the sum of the cubes all the way up to and including n, that formula is n squared over 4 n plus 1 all squared. We now need to find the sum of the series for which n is equal to 30. We will make use on a subsequent slide of this formula, that it is the sum of the numbers consecutively up to and including n, and this one is the sum of the cubes of the numbers consecutively up to and including n. We now need to find the sum of the series for which n is equal to 30. 1 all the way up to 30, and we know the form that the result will have. We will take the formula, substitute n is equal to 30, and simplify the arithmetic expression, and the expression was found to be the square root of this one on the previous slide. So it is going to be n over 2 multiplied by n plus 1. So there is our formula, and we will substitute n for 30. So 30 over 2 is 15, and 30 plus 1 is 31. So 15 multiplied by 31, and your answer is 465. I am certain that the examiners are expecting the alert candidates to make much more of this problem than just the solution of a mathematical puzzle. Look at the two different mathematical series presented and the formula for their sums. We will take a microscopic look at the two formulae and the associated series. So that is the first one. 1 plus 2 plus 3 all the way to n. That gives n over 2, n plus 1. And what about the other one? 1 cubed plus 2 cubed plus 3 cubed all the way up to n cubed. N squared over 4, n plus 1 all squared. So let us take a good look at them. As a matter of fact, we discovered already that here we have representations of it, that when we have the sum of cubes, which is this one, all we need to do is take the square root of it and we have the sum of the numbers all the way up to and including the final one. The first one is telling us that if we take any set of consecutive counting numbers, the formula may be used to determine their sum. So this is the consecutive counting numbers, and this formula is used in order to determine their sum. For example, if we take the first 20 counting numbers, all that we need to do is substitute 20 in the place of n, and we will be able to determine the sum of the first 20 consecutive counting numbers. So do that. 20 over 2, 20 plus 1. 2 into 20 is 10, and 20 plus 1 is 21. 10 multiplied by 21 is 210, and that will be the sum of the first 20 consecutive counting numbers. This is a result that we need to remember, 210. Those are your formulae again. The second formula is telling us that if we take any set of consecutive counting numbers, the formula may be used to determine the sum of their cubes. So take 1, 2, 3 up to n. The formula is used in determining the sum of their cubes, which is this formula. For example, if we take the cubes of the first 20, all that we need to do is substitute 20 in the place of n, and we will be able to determine the sum of the cubes of the first 20 consecutive counting numbers. 20 over 4, 20 squared over 4, 20 plus 1 all squared. That is the result. Now, let us take a second look. Let us return to the next slide, the previous slide, and see when we added the numbers from 1 to 20 what the result was. The result was 210. Now this one is 44,100. I am sure that by looking into the formula we can see that we are multiplying 100 by 441. 20 squared is equal to 400, which we divide by 4, resulting in 100. We have 21 inside of the brackets that we square to give 441. So 100 multiplied by 441 is 44,100. And what we have just done in that little short line is show you how we may arrive at the values without using a calculator. +20 plus 1 is 21, And we know, since we have been working with this problem, the square of 21 is 441. And we know that the square of 20 is 400. 400 divided by 4 is 100. 100 multiplied by 441, 44,100. So we could have done that calculation without accessing or making use of our calculator. So this is the result that we have right here. And do not forget that the one that we have was 210. Do not forget that, 210. However, we did not need to use a formula like that. Take a look at both formulae. So we did not need to use a formula like that. Take a look at both of them. It is plain to see that one is the square of the other. And that is what the second part of the problem was trying to establish. That one is the square of the other. But a little bit of it was left to be seen by us. Note that whatever we have in the first is squared in the second. N squared. 2 squared is 4. N plus 1 r squared. So notice that what we have in every single case is, in this particular case, what we have here, every single one of these is a square of the ones that we have there. So know that whatever we have in the first is squared in the second. Remember also that 4 is the square of 2. We did not need to use the formula in order to find the sum of cubes. If we have the sum of a set of consecutive counting numbers, we may find the sum of their cubes by squaring the result. So if we have the sum of all the numbers up to 20, we have 210. That is 210. So after that, we did not have to go through the formula to get the result here. All we needed to do was square the 210, and this would have been the result. So there's a relationship between the sum of the consecutive numbers from 1 to 20 and the sum of their cubes. If we can find the sum of those numbers, the sum of their cubes may be found by squaring the result. So 210 squared is equal to 44,100. This 210 is the sum of the numbers up to 20. And 44,100 is the sum of those cubes from 1 to 20. And how are these related? We square this, and this is the result. We have a pair of simultaneous equations which we may take any of two approaches in solving. We may make y the subject of each formula and equate the right hand sides. So we have this individual y right here and 1 right here. So transpose both of them, making y the subject. And what do we know? Transpose the first one. Y will be positive on the left hand side, x squared will be negative on the right hand side. So take this over. Positive y, take this one over negative x squared. So y is equal to 4 minus x squared. What about the other one? Cause the y to stand still and transpose 2 to the other side. So we have x minus 2 is equal to y. So y is equal to x minus 2. See? X minus 2 is equal to y. Then what? Y is equal to x minus 2. Both right hand sides are equal to y and are therefore equal to each other. See? Y is 4 minus x squared. Y is x minus 2x. If this is y, and this is why these two must be equal. So x minus 2 is equal to 4 minus x squared. Create a trinomial on the left hand side by transposition. So we have this negative x squared, this positive 4 minus 4. So negative 2 minus 4 is negative 6. This x will remain. So we have x squared plus x minus 6, and we need to determine which two numbers multiply to give negative 6, and when we add them the result is a positive 1. So we have x plus 3, x minus 2 is equal to 0, and the solution of which will give x is equal to negative 3, x is equal to 2, for which we need to find two corresponding values of y. In order to do that, we substitute the result into one of the other equations, and we have the one that we are substituting in highlighted right here. So x is equal to negative 3, so y is equal to negative 3 minus 2. Rule 2 in the manipulation of directed numbers: when we have numbers and we are adding them, the signs are the same, we add the values and the answer will take the same sign as the numbers that we have added. Then we have 2, x is equal to 2, y is equal to 2 minus 2, that is equal to 0. So y is equal to 0. We cannot just put negative 5 and 0 down as we have just done right here. We have done this because we are not through with the solution of the problem. When x is equal to negative 3, y is equal to negative 5. And when x is equal to 2, y is equal to 0. Now we will take the other approach in solving this system. On this occasion, we will make use of the fact that the first expression is equal to x squared and the other is equal to x. The first left hand side is therefore equal to the square of the second left hand side. So we have x squared is equal to 4 minus y, and x is equal to y plus 2. This is x squared, this is x. Therefore, this one is the square of this. So square this one and equate it to this. So we have what? 4 minus y is equal to y plus 2 all squared. And we will make use of what we know as the perfect square. So remember the expansion of the perfect square, where in finding the square of y plus 2, we square y. The middle term will be 2 times the first times the second, and then we have the square of the second. So square y, we get y squared. 2 times y times 2 is 4y, and then we have the square of the other term. So square y, y squared. 2 times y times 2, 4y. Squared 2, we get 4. So we have y squared plus 4y plus 4. And of course we have y, we have 4 minus y on the left hand side. Create a trinomial on the right hand side by transposition and turn the equation around. As a matter of fact, we just have 2 terms. So transposing this, we have a positive y, so 4y plus y is 5y. The 4's are gone, and then we have y squared. Turn around. y squared plus 5y is equal to 0. This is simple one-step factorization. And what do we know? Y is equal to 0 or negative 5. That we will put into the same equation as we did before. So we have x is equal to, let's see, the value of y is 0, x is equal to 0 plus 2. X is equal to 0 plus 2, x is equal to 2. And on the other hand, we have a negative 5. X is equal to negative 5 plus 2, x is equal to negative 3. We have the same thing. When x is equal to negative 3, y is equal to negative 5. And when x is equal to 2, y is equal to 0. It is good if we are able to look at one thing in two different ways. In the end, the second method proved to be more efficient in terms of the number of steps and possibly the time taken. The second method requires the application of the perfect square, which might require expansion or writing from memory. The perfect square makes it a bit risky, but being skillful with it is to our advantage. If we are skillful with the perfect square, then we have a short solution both in time and in the number of steps. If not, we will have no difficulty arriving at the answers. We may just say that the application of the perfect square may be a bit risky because some students might not remember to include the middle term of the perfect square. It is by the process of completing the square that we will write the quadratic expression in the form, this form that we have here, a x plus b r squared plus q. By completing the square, we will achieve that. Take 3 as a factor of the first two terms. This will cause the coefficient of x squared inside the bracket to be 1, and of course the middle coefficient will be affected as we see right here. 3 into x squared is x squared. 3 does not go into 2 exactly. We put that over 3, and the constant value at the end is the same. Take half of the middle coefficient and square it. Half of 2 over 3 is 1 over 3. Square 1 over 3, we get 1 over 9. Compensate for the new term. The new term is 1 over 9. We have 1 over 9 that was not there before. We need to remove it. But before we remove this 1 over 9, we need to multiply by 3. 3 multiplied by 1 over 9 is 1 over 3. We need to eliminate 1 over 3 minus 1 over 3. Write the whole number as a fraction with the same denominator as the fraction, and write the expression in the bracket as a perfect square. So, write this expression as a perfect square. What do we square to give x squared? X. What do we square to give 1 over 9? 1 over 3. So we have 3 times x plus 1 over 3 all squared. Now this we need to combine with this. So we say 3 times 1 is 3, and we put it over 3. The denominators are the same, so we can subtract this quite easily. And of course, no difficulty in seeing that 3 over 3 is still 1. Only that the denominators make it easy to perform the subtraction operation. So we have 3 x plus 1 over 3 all squared plus 3 minus 1, 2. So that is 2 over 3. In order to determine the minimum value, we may just take note that the minimum value is the constant value that we have right here. The minimum is 2/3. The minimum occurs when the expression inside of the bracket is equal to 0, where x plus 1 over 3 is equal to 0, or x plus 1/3 is equal to 0. Solve this simple equation, we get x is equal to negative 1/3. The value of x at which the minimum occurs will also give the equation of the axis of symmetry. So the equation of the axis of symmetry is x is equal to negative 1/3, because the axis of symmetry coincides with the value of x at which the extreme value is located. First, find the time at which the speed of the car was 40 kilometers per hour. In order to find the time at which the speed of the car was 40 kilometers per hour, go to 40 on the speed axis and draw a horizontal line to meet the graph. 40, meet the graph, then we go down. When we go down, what do we know? The time is 10:45 a.m. Here, the journey began at 8 a.m. and notice that 1, 2, 3, 4. So we have 4 of these little blocks for each hour. Therefore, if 4 of them is for each hour, then 1 of them will represent a quarter of an hour. So we have beginning here 10, then 10:15, 10:30, and 10:45, no doubt. The area under the curve represents the distance traveled. The area is in the shape of a trapezium whose area is given by area is equal to b over 2 h1 plus h2. Do not forget that irrespective of what these look like, they represent the same thing. What are they representing? The 2 parallel sides. And this b could have been j or h. It is representing the perpendicular distance between the 2 parallel sides. So h1 and h2 are the 2 parallel sides. Could have been any symbol. They are the 2 parallel sides. Those numbers that we have, or what we have inside of the brackets all the time, they symbolize the 2 parallel sides. And this b, whatever we have, whether it is a bk, a Greek letter lambda, or phi, it represents the perpendicular distance between the 2 parallel sides. The 2 parallel sides we have to be from here to here, that is from 8 a.m. to 11 a.m. is 3 hours, and then from 8 a.m. to 10:30 a.m. is 2.5 hours. No doubt, the perpendicular distance between them given by 80 on the speed axis. The result is 220 kilometers. 2 into 80 is 40. And 5.5 times 40, that can be done mentally. 5 times 40 is 200. And a half of 40 is 20. 220, that's all there is to it. Average speed is equal to total distance divided by total time. The total distance we have just calculated, 220 kilometers. The total time is all of 3 hours. Divide that, we get 73 1/3 kilometers per hour. Take note that each hour on the axis is divided into 4 squares, as we have mentioned before. Each square therefore represents a quarter of an hour. Note also that time begins at 8 a.m. and ends at 11 a.m. and that is a total of 3 hours. What do we need to find first? We need to find the angle CBD. The angle CBD may be found by making use of the fact that angles at the circumference that are subtended by the same chord are equal. We may also say that angles in the same segment are equal. So here is our chord. This angle goes to the circumference and back. This one goes to the circumference and back. They are equal. So those two angles are equal. They are angles in the same segment or angles that are subtended by the same arc or chord, and they are located at the circumference. Now we need to find another angle, CAB. CAB is analogous to the first. Actually, finding CAB is analogous to finding CBD. However, we have to first make use of the fact that opposite angles of a cyclic quadrilateral are supplementary. We are actually finding CAB, CAB. We are actually finding this angle. And this angle that we are finding, we may make use of the fact that angles in the same segment are equal. Same chord, go to the circumference and back. Go to the circumference and back. These two angles are therefore equal, as we can see. But we cannot tell what this one is without telling what this one is. This angle is 80. Opposite angles of a cyclic quadrilateral are supplementary. They add to give 180 degrees. So let us see cyclic quadrilateral. All 4 vertices are touching the circumference of the circle. This is a cyclic quadrilateral. That makes the angle that we have here, that is 80, supplementary to this one, not the 71 degrees, to all of this. So this large angle here is equal to 100 degrees. 80 plus this large angle is 180 degrees. No one can help but say that this large angle is 100 degrees. BDC is the remainder after subtracting 71 degrees from 100 degrees. So BDC, this is 100 degrees, take away 71, we end up with 29, that is 29. Then we may go merrily along to say that what? The angles in the same segment are equal, so that is 29, that one is also 29. Angles in the same segment are equal, are angles that are subtended by the same arc or chord at the circumference, they are equal. So CAB is 29 degrees. We need now to find the length of the side of the triangle BD. The chord BD is a part of this triangle that we have right here, and this triangle is jam-packed with information that will cause us to be able, for a certain, to be able to determine the length of the chord BD. In finding the length of the chord BD, we will make use of the sine rule. The chord AB, which is equal to 9.5 centimeters, is opposite to the angle, which is 71 degrees. And BD, which is this chord, is opposite to this angle. This angle is actually the sum of 41 degrees and 29 degrees. 41 plus 29 is equal to 70. Now, sine rule makes use of side and opposite angle, side and opposite angle. 9.5 is opposite to 71. BD is opposite to the sum of these two angles. By transposition, we have BD is equal to 9.5 sine 70 over sine 71. And I will not be amazed to discover that this result is a wee bit smaller than 9.5 centimeters, because the sine, well, the angles are very close. So we imagine that the answer could not be too far away, and that is equal to 9.5 centimeters. We will make use of the cosine rule in finding the angle theta. Be aware that OA and OB are radii of the circle and are therefore equal. There we have 5 centimeters, 5 centimeters. These are equal, and we will make use of the cosine rule. The second version of the cosine rule that makes use of 3 sides of a triangle in order to form a particular, or to find a particular angle. That is our cosine rule. A bit cumbersome, but very simple. The 2 sides that form the angle are the 2 that we will add here. The one that is opposite to the angle is the one that we will subtract. And then again, we have 2 times the product of the 2 sides that form the angle. That is not very difficult. So theta is to be found, the 2 sides that form the angle, 5 squared plus 5 squared. Then we minus 6 squared over 2 times 5 times 5. When we simplify, square of 25, square of 5, square of 36, 2 times 5 is 10 multiplied by 5 is 50. Then we have cos theta is equal to 0.28. Do not forget that when we have the cos of an angle, we can find the angle by taking the cos inverse, and we may do that on our calculator. The result is 73.7 degrees. And that is written to 3 significant figures as requested in the statement of the problem. Next, we need to find the area of the triangle. The area of any triangle may be found by taking half of the product of any 2 sides and multiplying the result by sine of the angle that the 2 sides form. If we have a triangle and we have 2 sides and the angle that the 2 sides form, the area is going to be half of the product of the 2 sides. We are using that, half AB sine C. A and B are the 2 sides that form the angle C. So half of the product of any 2 sides, multiply that by sine of the angle that the 2 sides form. The 2 sides in this particular case are these 2 sides, 5 centimeters, 5 centimeters. The angle that they form is 73.7 degrees. Throw those in, and what comes out is the area of the triangle that we find to be 12 centimeters squared, and we are writing that correct to 3 significant figures as requested in the statement of the problem. Next, we are required to find the area of the disk that was cut off. In order to find that area of the disk that was cut off, we need to find the area of the sector associated and subtract the area of the triangle that we have just found. So let us go straight ahead and find the area of the sector of the circle. And it is a fraction of the area of the circle. And the fraction is given by the associated angle divided by 360 degrees. So the angle associated with the sector over the angle associated with the circle, the angle of an entire revolution, 360 degrees, and that we will multiply by pi r squared. (73.7) over 360 multiplied by pi multiplied by r squared. So the angle over 360 times pi r squared. That turns out to be 16.0 centimeters squared, 0.0, because of the three significant figures that are required. Now, from this area, we will subtract the area of the triangle, and the result will be the area of the disk that was cut off. And is required to be written to three significant figures. We have included 2 decimal places in order to make certain of that. Here we have a transformation represented by the matrix M, A, B, C, D. It transforms the point 1, 4 to its image negative 4, negative 1. It also transforms the point 3, 5 to its image negative 5, negative 3. The matrix of transformation is used to multiply the position vector of the point that is being transformed. The result will be the position vector of the image. The first equation should demonstrate an application of that principle. What principle? The principle that when we multiply the matrix of transformation by the position vector of a point, we end up with the position vector of the image. The second is analogous to the first. The matrix of transformation will multiply the position vector of the point, and its image will be the position vector negative 5, negative 3. Find the values of A, B, C, and D will be synonymous to finding the matrix M. In finding M, we may take an approach in which the two equations are converted to one equation. So take this, we have A, B, C, D, first column 1, 4, 1, 4. Second column 3, 5, 3, 5. Equal to the first column negative 4, negative 1. Second column negative 5, negative 3. We will proceed to solve the equation on the next slide. Here we have the original problem. In finding the matrix M, we will eliminate the matrix from the left hand side. By so doing, its inverse will multiply the matrix that is on the right hand side. The inverse of which one? The inverse of this matrix. There we have it. The matrix multiplication is not commutative. The matrix comes after the matrix M. So this matrix comes after the matrix M. This one. on the left hand side. On the right hand side, its inverse must also come after the other matrix, which is this one. So clarifying that, we are saying we are finding the inverse of this matrix, which we will multiply on this side. But this matrix comes after the matrix M on the left hand side. Therefore, its inverse will come after this matrix on the right hand side. The inverse of this matrix is a combination of its adjoint that we have right here and the inverse or the reciprocal of the determinant of this one. So the determinant 1, 5 minus 3, 4. The reciprocal of the determinant is right here, and we have the adjoint all the way over here. The adjoint needs to be coming after this matrix on the right hand side, because the matrix originally is after the matrix M on the left hand side. The reciprocal of the determinant does not come after, but is placed before the matrices. It is a scalar, not a matrix, and its position will not affect the result. Notice that although we are intending to put the inverse of this matrix after this matrix on the right hand side, we are placing the reciprocal of the determinant in the front. The reciprocal of the determinant is a scalar. By multiplying by a scalar, what do we know? The scalar product is commutative. The scalar may therefore be placed at any location, as its position will not affect the values obtained. Now we have negative 4, 5, negative 5, negative 4. Row by column. Row by column. The upper with the left, the answer goes to the upper left. Negative 4, 5, negative 5, negative 4. The upper with the right, the answer goes to the upper right. Upper right. The answer goes to the upper right. So negative 4, negative 3, negative 5, 1. There we have it. Now the lower row, the lower with the left, the answer goes to the lower left. Negative 1, 5, negative 3, negative 4. Right there. And finally, the lower with the right, the answer goes to the lower right. Negative 1, negative 3, negative 3, 1. And that's all there is to it. In simplification, we get 1 over negative 7, 0, 7, 7, 0. And the arithmetic operation at the end will not be too difficult. So A is equal to 0, B is equal to negative 1, C is equal to negative 1, and D is equal to 0. We need to determine the transformation, or to describe fully the transformation that is represented by that matrix. So let us write the matrix down. A in the place of A, B in the place of B, C in the place of C, and D in the place of D. What transformation does this matrix represent? In describing fully the transformation that the matrix M represents, let us make use of the fact that in forming the matrix of transformation, the points 1, 0 and 0, 1 are written as the two columns of a 2 by 2 matrix and subject to the transformation. The resulting matrix is the matrix of transformation. Take the point 1, 0 and 0, 1 and write them as the columns of a 2 by 2 matrix. Subject 1, 0 to the transformation, and what is the result? 0, negative 1. So 1, 0 goes to 0, negative 1, and 0, 1 goes to negative 1, 0. Which transformation is responsible for that? For what? Let's see what we are talking about. Notice that what? According to the requirements of the derivation of a matrix of transformation, 1, 0 will go to this one, 0, negative 1, like so, and 0, 1 will go to negative 1, 0, like so. And we need to determine the transformation that is responsible for causing this point to go like this and this point to go like that. When the motion of the 2 points are parallel to each other, we expect a reflection. In a reflection, the line joining points to their images are parallel to each other, and the same is true for translation. This is not a translation because a translation is represented by a column vector. We are sure that the matrix of transformation is a reflection because 1, the line that join points, the lines that join points to their images are parallel. We have 2 transformation with that property. 1 is translation and 1 is reflection. We are sure that we are not talking about a translation because a translation is represented by a column vector, not a 2 by 2 matrix. M therefore represents a reflection in the line y is equal to negative x. So this one is reflected on this perpendicular to the mirror line, and this one is reflected perpendicular to the mirror line, like so. There we have 3 points and the origin, 4 points in all. OP is the position vector of the point P. All we need to do, since we are talking about the vector OP, we know that it is a position vector of P, is a vector that goes from the origin to P, and that may be determined by writing the ordinates of P in a column form. That is the position vector of P. Let us make use of the triangular law in finding the vector RQ. What is RQ equal to by triangular law? RQ is equal to OQ minus OR. Substituting the vectors, and this is what we get. We get OQ minus OR. And what do we know? 6 minus 2 is 4, and 10 minus 8 is 2. We can already see that they are the same. The magnitude of a vector is its length, and we need to use Pythagoras' theorem in determining the length. And we need to determine the length of which vector? OP. So the length of OP is equal to the square root of 4 squared plus 2 squared. the square root of 16 plus 4 is equal to the square root of 20. That turns out to be 4.47 units. The magnitude is found by using Pythagoras theorem. Two relationships between the vectors OP and RQ are 1, they are parallel, and 2, they are equal in length. I'm just thinking that asking us to determine the magnitude of a vector kind of gives the problem away, because we are asking to find the length of OP, hinting us that the next one maybe not necessarily, but it is possible that a particular candidate might recognize that since this is the magnitude or length of the vector or length of the movement, distance of the movement, then in the next section that there might be some reference to length. And as a matter of fact, there is. So two relationships between the two vectors are 1, they are parallel, and 2, they are equal in length. Usually when we are asked the relationship between two vectors in CSEC, CSEC, it is because they are parallel. Usually we may use parts of a problem as a guide in solving others. We were asked to calculate the magnitude of a vector. We could have used that as a clue that the relationship between the vectors has something to do with length.